root mean square velocity. You see, this concept of root mean square is taken wherever there is sinusoidal fluctuation, or even you could say simple fluctuations also are considered for this purpose. While studying AC also, we come across this term root mean square value. Now, what this basically means is you take first square. We are talking about velocities. There are number of molecules, their velocities. Suppose molecules are n in number, then square the velocities, then sum up. Then you take the mean square. We are starting from the right side, square, then mean. Mean, that means you divide it by the whole number of molecules, that's n. Now, this is the mean square value. If you are going to write this much, it is the mean square value. But here we are concerned with root mean square. That means third process also will be involved, square, then mean. That means you take the average and then take the square root. This whole thing, when squared, this would be known as RMS value. Now, you might ask me why this is of concern for us while studying gases. You know, gas molecules have random velocities in different direction, and if you go to take the final average value, it's going to be 0. So that's why we take another alternative, we square. All the velocities when squared will become positive, then take mean and root. Root mean square value will be given with the formula VRMS. This is root 3 RT by M. This is the basic and most prominent equation of the chapter that will establish the superiority of kinetic theory, because it defines RMS velocity and it relates it with temperature. But before that, one step, just let us know how this could be derived with the help of kinetic theory. This is total mass upon volume, it will be density. So you also know one relation for the pressure in terms of density. But remember, here we take the square mean velocity. It's not RMS, it is square mean velocity. As already you know from the ideal gas equation, PV equal to nRT. Here N0, I am taking the number of moles as N0. So, in place of PV, we could write N0RT. With this equation, PV, that is N0RT, it's going to be 1 by 3 total mass V square bar. This would be 3 N0RT by m, but m here is the total mass. Mass of one molecule is m, that of n molecules will be m into n. So, this is V square bar. You see, this is total mass upon the number of molecules. This will give you the number of moles. This is n we are taking for number of moles. So, this is total mass, and N0 R T 3 upon MT. This could be written as this one, molecular weight, because mass of N0 mole is MT, then that of 1 will be MT by N0. So, here we could write the molecular mass, molar mass, whatever you call it. Sometimes it's also read as molecular weight. So, RMS velocity will be root 3 RT by M. This is what we had to derive. Then one more thing is there, that we have studied RMS velocity, but does it really serve the purpose of our study and requirements? No, not the least. Actually, there was a scientist, Maxwell, He has so many contributions, but one thing he gave us very important, that is the distribution of velocity. That's known as Maxwellian distribution of velocity. He plotted a graph between the velocity and the number of molecules. Number of molecules at that particular velocity. He plotted the graph between the number of molecules at a particular velocity and the velocity concerned. This type of graph was obtained. You see, maximum number were found at one particular velocity, that is known as most probable velocity. Its value is found to be root 2r t upon m. Remember, it's not 3. Then the average velocity is another term that's shown by V bar, or you might say mean velocity. The number of molecules at this very velocity is still less. This should be known as n bar. Here, this will be known as nmp. And most astonishingly, surprisingly, the number of molecules at RMS velocity were found to be minimum amongst these three. So, what we initially imagined, that by studying RMS velocity, we are going to get something very peculiar, but no, it was not the case. The maximum number of molecules were found at a particular velocity, that's known as most probable. Average velocity is given by this relation, 8 upon pi r t by n. Then RMS velocity, you already know, this is root 3 r t by m. Obviously, if you compare, you'll find RMS velocity is maximum in these three. Then there is average, and then finally most probable velocity. At the same time, if you compare the number, you'll find the number at most probable is maximum, then that is at average, and RMS velocity molecules will be quite less in number. Remember, this whole graph is known as Maxwellian distribution of velocity. Then finally, the kinetic theory gets wide application in explaining gas pressure, effusion, diffusion, concept of temperature, energy, and above all, it is most useful and considerable relevance it has in thermodynamics.